In this video, we're going to look at unidirectional control of a DC motor. So the DC motor in this circuit is represented by this symbol here, the circle with a capital M in it, and it's got these two terminals on it. DC motor can be driven in either direction by passing the current one way or the other through the motor. In this case, we're going to be controlling it with an Arduino Nano. We've got a digital output pin here, D3, which is going to be switching the motor current on and off. The Arduino Nano can't supply enough current from its digital I/O pins to drive the motor directly, so we're going to use a transistor to interface between the two devices here. So pin D3 here is going to feed a signal into this MOSFET transistor to switch it on and off, and when it's switched on we'll get a current flowing down through the motor, and when it's switched off the current through the motor will die away. So the specific transistor that we're using here is an N-channel MOSFET. It's called IRFZ44N. It's got three terminals, so MOSFET has got gate, drain and source or terminals. Those are the names that are used for them. So we'll see the code for a minute, in a minute rather, to see how the Arduino actually changes the voltage on this pin in order to switch the motor on and off. Some other features of the circuit here, there's a diode here which we call a flyback diode, and this is there in order to allow the current through the motor to sort of die away slowly when the transistor switches off. So rather than suddenly interrupting the current through the motor, we need to allow a way for that current to just die away in its own time, basically dissipate the energy that's built up in the magnetic field of the inductance of the motor. So if you don't use a flyback diode here, there's a danger when you suddenly switch off the current in a motor that you'll generate sparks in the circuit, because the inductive nature of the motor will want to continue the current and not see the current change very suddenly from a high value to zero. So that's the purpose of the flyback diode here. It kind of prevents voltage spikes in the circuit. I've also got an indicator LED in my circuit here, which I think is always useful to include when you're trying out a circuit like this, to put something in there which can provide some visual feedback. It just enables you to check that the Arduino is actually running correctly, and you can also use it to provide visual feedback for like times when the motor should be on or times when it should be off, so that you can see if there's a problem with the circuit. You know, if you know that the signal coming out here should have the motor turning but it isn't, it can be useful to know what part of the program you're in, so the LED will be useful for that. I've got a 6-volt DC power supply here, so this could be a battery pack, which is what I'm using, but it could also be a bench power supply or something like that. I've got a capacitor here, 220 microfarad electrolytic capacitor. So this is connected between the rails of my circuit, and the purpose of that is to act as a kind of a buffer for electric charge to damp down any voltage spikes that get generated on the voltage supply rails of the circuit. One of the characteristics of motor control circuits is that when you're switching the motor on and off a lot, because it's an inductive load, it does produce a significant amount of voltage interference on the supply rails, and the capacitor will tend to sort of damp down that effect a bit and smooth out the voltage supply, which will benefit the Arduino. What we don't want is for large voltage spikes here to disrupt the operation of the Arduino. If they were very severe, you might find that the microcontroller on the Arduino would reset sometimes unpredictably, so this will help to prevent that. Okay, so let's have a look at what the physical circuit looks like, and we'll compare the parts of the physical circuit to the diagram. So here's my breadboard. I've got this connected through a USB cable back to the PC as well. Try and position this so we can see things at the same time. So I've got the motor here. I've got a little wheel attached onto it with a piece of tape just so we can see when the motor is turning. This motor is actually a geared DC motor, so it has a DC motor at one end, but it has a 120:1 ratio gearbox at the other end. So the wheel is actually going to turn relatively slowly even when the motor is spinning fast. And we've got 6-volt battery pack here, so this is a 4xAA battery pack with a built-in power switch, and I've got that battery pack connected directly to the rails of my circuit here, so I'm using the two rails on this side of the breadboard. So I suppose you could think of the red and blue rails on my breadboard here as corresponding to the 6-volt rail up here. That'll be the red rail, and the 0-volt rail down here, that's the blue rail on the breadboard. So I have them connected directly to my battery pack. That's essentially this part of the circuit here where the voltage supply is connected to the 2 rails. Also on my breadboard, you can see down in the corner here, I've got the 220 microfarad capacitor. That's this component here, and you can see it has one leg in the positive rail and one leg in the negative rail. So that's these 2 connections here. Now this is a polarized capacitor, so it's important to make sure that you get the correct leg connected to the negative rail, and you'll see on most electrolytic capacitors the negative rail will be marked with a stripe down one side. Should be able to see that on this actually. There is a stripe down this side of the capacitor and it's got a minus sign on it, so that's the minus leg that will be plugged into the blue rail here. Okay, what else have we got? We've got the power connections for the Arduino. So the 5-volt pin on the Arduino is connected to the red rail, and I've used a red wire for that. So the 5-volt pin connects to the red rail. Anything you're connecting to the positive power supply in your circuit, you should always use a red wire for that. And never use a red wire for anything other than the positive supply voltage. The other connection here for power to the Arduino is the ground pin is connected to our negative rail. So that's this black wire. And similarly, we use black wire for the negative supply voltage, normally 0 volts. And we only use black for that. So anywhere that you've got a 0-volt connection in the circuit, it should be a black wire, and you should never use black wire for anything else. Okay. My little LED circuit here is coming from pin D2, so that is this green wire. If I can move this over here, maybe it'd be easier to see this. So I've got one green wire here which is connected to pin D2 on the Arduino, and that is connected to my LED, and it feeds current through the LED through this resistor here. And actually I noticed that is connected in the wrong place, so I'm just going to fix that. So that resistor should connect from one of the LED pins down to the negative rail here, which is ground. So on our circuit diagram, that's this part here. So the green wire coming from D2 to the LED is this wire here. This symbol here is my green LED. That LED is connected through one of the rows of the breadboard to the resistor. That's this connection here. This symbol here is the 220 ohm resistor, which I have just here on the breadboard. And then the resistor connects directly to the rail down here. Okay, so this component here is our transistor, the IRFZ44N. You can see it's a big chunky kind of power transistor, so it's got this kind of metal back plate on it with a hole in it for bolting on a heatsink. So if you were using this in a high current application where it was going to be dissipating a significant amount of power, you can bolt on a heatsink here so that it doesn't actually burn out. In this case it's not required because there's not going to be that much current going through it. So I've got the transistor there, and I've got the flyback diode. It's this kind of black cylindrical component with the 2 legs. Again, this is a polarized component because the diode is like a one-way valve for electric current, so you do need to be sure that you get the negative terminal of the diode connected in the correct, get the correct ends the right way around. So the negative leg of the diode in this case is actually connected to the positive rail, which can seem a bit counterintuitive, but it's because of the way it's being used here as a flyback diode. What you're trying to prevent is the voltage at this terminal of the motor spiking up very high. So actually if there's any danger of that happening, this diode begins conducting and allows current to circulate around this loop. So the negative leg of the diode is the one marked by the kind of silver stripe at one end of the diode. It's a little bit hard to see it here on camera, but it's easy enough to see in real life. You'll see there's a grey kind of silver stripe at one end of the diode. So that's the end that will connect to the positive rail up here. And I have it connected to the red rail on the breadboard. The other leg of my diode is connected to one of the terminals of the motor and also to the drain of the transistor. So to figure out which of the pins are which on the transistor, what you really want to do is look up the data sheet for it. So let's have a look and see how you would go about doing that. I'll open up a tab in the browser here, and I'm just going to type in IRFZ44N, that's the name of the transistor, and the word data sheet. And Ideally, we're going to be looking for a PDF result. So let's have a look at, well, we just tried the first one here, I suppose. Yeah, so you can see here is a data sheet for one of the versions of this transistor. So hopefully this one has got the pins in the correct order, the same order as what we're using here. Now I'm just trying to see, is there a pin out here to say which pin is which? I'll try one of the other data sheets. That one is not very clear. Let's try this. Yeah, this is better. So again, this is another data sheet from a different manufacturer, but for the same type of transistor, IRFZ44N. And you can see that it includes a picture of the transistor here with the pins numbered, and then it explains which one's which, gate, drain and source, so that you can match it up with the different terminals on the circuit symbol. So when you're putting together the circuit yourself, you need to be careful to look at the datasheet to make sure you get the correct pins in the correct order, gate, drain and source. So I have that on my breadboard here, and I've also got my motor connected in. So I've basically made all of the connections that I have on the circuit diagram here. And now we're ready to program the Arduino and start controlling the motor. So I'll just try and sit this flat so we can see that when it starts turning. And I'm going to bring up, maybe I'll move that over a little bit so we can see the Arduino code at the same time. My battery pack is already switched on there, so it's just going to be a matter of actually programming the Arduino to switch on that one pin. Now initially, let's just check the LED before we do anything else. So I'm just going to make pin D2 a digital output, so that's the LED pin. And we'll just switch it on and off a couple of times. So this is really just to check that the Arduino is functioning correctly. So I'll program this on to the Arduino. And you can see the LED switching on for a second and then off for a second repeatedly over and over and over again. So because I put these instructions into the loop function here, it's going to carry out these instructions in the order that I've listed them. But when it gets to the end, it's just going to repeat them again, and it'll repeat them over and over and over. Now it is necessary that we make pin 2 a digital output, because if you want to control the voltage on a pin from the program, the Arduino can only do that to pins which have been configured as digital outputs. That's why I've made pin 2 an output. What I'm going to do in the program now is I'm going to add an additional digital output on pin D3 so that I can also control the motor. So pin mode 3 output. So now configure pins D2 and D3 as digital outputs. I suppose what I'll do here is let's alternate between having the LED on or the motor on. So let's say LED on for 3 seconds. And during those 3 seconds, I'm going to make sure the motor is off. And then I'm going to do it the other way around. So LED off and motor on. And I'll do that for 4 seconds as well. Okay, so we're going to go through 2 phases here that'll alternate repeatedly. In the first one, we've got the LED is on and the motor is going to be off. So pin D3, the voltage will be low, which is going to switch off our transistor. And when the transistor is off, the current through the motor is going to be off. And we're going to leave things that way for 4 seconds. And at the end of the 4 seconds, we're going to switch the LED off. We're going to switch the motor pin on, which is going to switch on the transistor. And that's going to allow the current to flow through the motor and start it turning. And we're going to leave it that way for 4 seconds. So let's upload this to the Arduino and hopefully we should see the motor responding. So the LED first comes on for 4 seconds, and at the end of that the LED goes off and we see the motor turn for 4 seconds. Then LED for 4 seconds, and then motor for 4 seconds. And this cycle is just going to repeat indefinitely. Okay, so what we might do next, just to quieten that thing down first, I'm going to get rid of this bit for a second, just so we have the motor off. Okay, now what we're going to look at is speed control of the motor. So we just outputted a digital signal that time from D3, which is either on, which fully switches on the transistor, or off, which fully switches it off. And we can see the motor was either turning or standing still. Now what I'm going to do is I'm going to send a pulsed signal into the transistor here. So instead of constantly switching it on, I'm going to switch it on and off very rapidly, which means that we're going to deliver current pulses to the motor rather than a steady current. We're going to be switching on and off the transistor, which is going to sort of speed up and slow down the motor, but it's going to happen so fast that we won't see the motor actually switching on and off. It won't have time to actually come to a standstill and then to begin moving again in between the switching cycles. It's going to be switching on and off hundreds of times a second. So as a result, we'll just see kind of more like the average speed of the motor. Now, actually on a very short time scale, it is kind of speeding up and slowing down, but it's just going to be hovering around an average speed, and that's what we're going to see. So to control or to produce a stream of pulses on pin 3, it still needs to be a digital output, but I'm going to use a different function here. Rather than digital write, I'm going to use a function called analog write. And analog write, you tell it which pin, and then you give it a number between 0 and 255, and that's going to control the length of the pulses that are delivered to the motor. So the frequency of pulses, by which I mean the number of pulses per second, is going to be constant, but we can vary how long each one of the pulses lasts. And if we make the pulses longer, that means we're delivering more power to the motor, so we'll see it speed up. If we make the pulses shorter, we're delivering less power to the motor and we'll see it slow down. So let's put in, let's start it off at full speed. So the maximum we can put in here is 255. The reason it's 255 is that's the highest 8-bit unsigned integer. So we do that for 4 seconds. I'll need to fix these comments. So this one is going to be motor on fast. Next one is going to be, let's do LED off and motor on slow. So in this case, I'm going to put in half pulses that are half the length, so half the maximum length. Now this essentially corresponds to what we call a 50% duty cycle. So the duty cycle refers to the percentage of the time that the pulses in a pulsed signal are high. So if they're high for half of each cycle, then that would be a 50% duty cycle, and that's what 127 is, very close to half of 255. So that will be the second thing we're going to do, and then let's put in a third one. So we'll have LED off and motor stop. So for motor stop, I'm just going to send in pulses that have got a duration of 0. So this is 0% duty cycle. You can kind of think of it as if it's sending the same number of pulses per second, but in this case the duration of each pulse is 0, so we're actually not delivering any power at all to the motor. So let's upload this and we'll see what the motor does in response. So forward 4 seconds fast. Now you can see it's going slower for 4 seconds, and then it should stop for 4 seconds. And it should repeat the same sequence again. Forward fast, forward slower, and finally stop for 4 seconds. I'm going to try and reduce this down to see just how slow we can make it. So for the slow part in the middle, I'm going to set that down to 50, which is about, it's just under 20% duty cycle. Sorry, no, it's just under 10% duty cycle, excuse me. So nice and fast. And you can see it's really crawling along there, and you can actually hear as well that it's making more noise because every time it tries to actually deliver a pulse of current to the motor, some of the energy is actually just causing vibration in the motor, but it's not managing to actually produce significant rotation of the motor shaft. So we're actually hearing some of the energy just dissipated as sound. Okay, so that's it. Unidirectional speed control of a DC motor. That's a good place to stop.